And I think the last session was a very nice introduction to what we're going to be doing now. So we're going to talk about technology, we're going to talk about irrigation, we're going to talk about saving water. And most particularly, the story I'll be telling you is the one of a technology that was, let's say, developed by the high-energy physics community for the high-energy physics community, so for the specific needs of the high-energy physics community. And what we've been trying to do for more than a year now is to apply this very same technology to water saving, or more generally to irrigation. So my name is Martin. I work at CERN, and I spend the vast majority of my time working for what we call a collaboration, and the name of this collaboration is CMS. So in the CERN jargon, a collaboration is essentially a group of people who pool their resources together to design, build, operate, and upgrade high-energy physics detectors. So first of all, I'm going to describe a little bit what this collaboration is about. Then I'll look at the technology, so this famous technology that we developed for our needs as high-energy physicists, and see how we can transfer that technology to irrigation solutions. And I'll introduce the Phosphori project that I lead and to give you a status and an outlook. So first of all, what is CMS First of all, as a detector, because as I said, a CMS is both a group of people, a collaboration, and a detector. This is a slide seen from the sky of CERN, so you can see the 27-kilometer accelerator, as Freddie showed before. So if you're familiar with the area, this is the Geneva airport. And the idea is that in this ring, we're accelerating protons, two beams, one running clockwise, the other counterclockwise. And these protons are smashed into each other in 4 locations. And one of these locations is right here, which is the CMS site. The detector itself is installed underground, about 100 meters from the surface, in a very big cavern that was excavated for that purpose. Now, so CMS stands for Compact Muon Solenoid, and this is a drawing of the detector. The idea of such detectors is that they are designed so that no particles that are created as a result of the proton collision can escape undetected from this detector. So this is why it has an onion layer, if you like. It's a series of concentric layers. And okay, on the drawing, it may not look very, very big, but before I go through the numbers, I brought this picture here. This is a picture taken of the cavern where the detector is now installed before it was actually installed there. And just to give you an idea, this is a human being. So this is the kind of incredibly big infrastructure that are required for our needs. And now, so if we go through the figures, so this is the diameter of this detector. It's like a cylinder, if you like, as with concentric detector layers. 14.6 meters in diameter, 21.5 meters in length. The weight is twice the one of the Eiffel Tower. That gives you an idea of the logistics to install that things 100 meters under the surface. It has a magnetic field of 3.8 Tesla, which is about 100,000 times stronger than the Earth magnetic field. We've got a magnet in there that is running, or that is operating at minus 268 degrees Celsius, so we've got a lot of cryogenics involved. We've got 51 million readout channels, so these are parameters that you read out all the time. And this cost about 542 million Swiss francs to build. Now, this, as I said, looks pretty big as an area where you want to put a detector. And the next picture is actually what it looks like once it's installed. And that's quite different, right? Now it looks very cramped, but it's exactly the same cavern. Just now, this time, the detector has been installed. Why are we building these detectors? Well, we want to potentially discover new particles through the analysis of the collisions. These detectors, as I said, are a series of detector layers. And because of the onion structure, every time that some particles are created at the very center of the detector, whatever direction they go, they will cross the various layers. And each layer will record a signature of the passage of the particle. right? So if you like, each layer will provide you a piece of information about the incoming particle. And it's when you put all these together that you reconstruct all these signatures in the different layers that you will get what we call an event, which is essentially like a big picture of what happened after the collision. And when you put all these together, this is what you get. This is a visualization of an event where you see some particles would have left signatures on the outer part of the detector, some of them in the inner part. Now, the project cycles in high-energy physics are very long. This is just a timeline to show you that the first idea was born in the late 90s, and this year we're celebrating the 25th anniversary of the first paper of the foundation of the CMS and Atlas, our competitors, let's say, detectors, right? So this is 1992 is where let's say a lot of momentum, enough momentum was put behind the project, and then it took a long time to design and build the detector, which started operation in 2009. And we are going to keep and operate this detector, hopefully, up until 2030. So that's the kind of project cycles we're talking about in our community. Now, as I said, CMS is a detector, but it's also a community. And here, as you saw from various presentations before me, we are blessed with a very large diversity among our colleagues. As of CMS, we're about 5,250 people working in this collaboration. We've got the bulk of it comes from the physicists. A lot of these are actually students. Then you've got engineers, technicians, and so on. In this region, in the Middle East region, we have institutes coming from the following countries: so Egypt, Oman, Lebanon, Iran, and Saudi Arabia. And this happens to be the building where we tend to meet when there is a conference at CERN. Now, the detectors that we've been installing and that we are now operating are fairly fragile. They have a great performance, but we need to be super careful in their operation. They don't deal very well with humidity. They don't deal very well with swinging temperatures. Some of our detectors need to be kept between 20 and 21 degrees. So again, remember the scale of the experiment, which is a challenge, with a dew point that is very important to control. The idea is that you don't want condensation on all these parts, otherwise this will damage the electronics. And some other detectors are even more complicated to run because they need to be cooled down. And the latest detector that we installed, that is these two pictures, need to be cooled down using CO2 as a gas at minus 20 degrees. That means that in order to ensure the performance and the safety of our detectors, we need to monitor the environment very carefully. The environment, by this I mean temperature, humidity, that sort of parameters. And all this has to happen in a very high radiation environment, because when the collision takes place, this is creating activation in the environment. So you've got, your sensors need to be able to cope with that. And if you go to commercial sensors, well, they are fried within minutes, right? So we had to come up with a solution that would allow us to monitor temperature, humidity, while coping with radiation. And so this is the famous technology that I want to introduce today. It's called fiber optic sensor systems. The idea is quite simple. Instead of having sensors connected by cables, you use fiber optics. And the fiber optics holds the sensors and does not need to be powered. It's just light going back and forth into the fiber. What we call bright grading is something that is not new, but that we have been developing further. The idea that you take a commercial fiber, really off-the-shelf fiber for telecommunication applications, for example, and you use a UV laser to introduce some defects in the core of the fiber. This will lead to reflections. So if you shine broadband light into the fiber, some of it will be transmitted, it will just keep going, but some of it will come back. And it will come back as a spike in a particular wavelength. And this wavelength is directly correlated with the spacing between these little mirrors, right? So if something happened to the spacing between these little mirrors, if they split, if they expand, you will have a shift in your wavelengths. So what you've got essentially is a way to measure temperature, the thermometer. If it's colder, this will shrink, the distance between your little mirror will shrink, and you're going to have a shift in the opposite direction. So it expands or it shrinks, and you see this spike changing, shifting. So that's fairly easy. This you can buy commercially. Well, what we really injected into all this was how to transform what is essentially a temperature meter into something else. And the intellectual property, I would say, the research is really embedded into what you can wrap around this sensor. Because if you use an hygroscopic material, for example, a material that will swell with humidity, then all of a sudden you don't have just a temperature, a thermometer or a temperature meter, you got yourself a humidity sensor. If you find a coating that you can wrap around your temperature sensor that absorbs helium or any gas, it's the same. It will swell when in the presence of this gas, and therefore this little spike in bandwidth will also shift. So you got yourself a detector that can measure the concentration of gases. And this technology has many advantages. As I said, because it was for us, for high-energy physics, the main one is that it's completely resistant to radiation, because it's essentially, well, it's sand, right? It's a fiber. It can cope very well to magnetic field, to dust, extreme temperatures, and electromagnetic interference. So it ticks all the boxes as far as we are concerned. But it's also very high sensitivity, lightweight. It's really just a commercial fiber. Extremely simple to install because you don't need to power it and you don't need to read down the data. This is just done with light. And it is long-distance readout. I mean, you can read out sensors up to 100 kilometers. Yeah? And again, as long as you understand how to coat the sensors, you can turn it into very different type of environment monitor. So you can do temperature, strain, humidity, and so on and so forth. Now, this fiber obviously needs to be read out. So it is plugged at the moment into, again, off-the-shelf pieces of equipment that are fairly expensive. I mean, this is $20,000. So this is obviously out of the range for commercial application right now. And once the data comes out of this, we call it interrogator. Well, of course, they need some processing and user interface, but essentially, this is a system that has been deployed at CERN for a long time, at CMS, and has proved extremely reliable. So, from temperature to humidity, we, at the very center of CMS, have a tracker, which is a silicon detector that can be extremely damaged by humidity. So this is why we developed this particular type of sensors, so humidity sensors. The idea is that the molecules of water will be trapped into a coating, a polyamide film, essentially. There will be this swelling effect that I meant. And here you can see what you get at the output. So the difference between the red and the blue is essentially humidity changing, which means that your wavelength is shifting too. Yeah. Now, we installed a lot of these into our tracker detector, and this has been running for a long time. It's quite efficient. Now, the idea behind all this is, what if we were to take these sensors, take this system, bury the sensors in the soil, connect it obviously to the same system, and use it to optimize irrigation, meaning that you only deliver water when it's needed. So by monitoring the amount of water in the soil, you can decide whether this is sufficient for the crop to grow efficiently. And also, not when your soil is saturated with water because of irrigation, you just shut down the water. You don't waste it. It doesn't, you only provide it when it's needed. So also, we do believe that at the time already, we believed that if we manage to provide water exactly at the right time, we might even be able to increase the yield of the crop because we kind of optimize its growth environment. Another advantage too is that you can run these fibers over tens of kilometers. So if you are in a landscape where the fields are not adjacent, they are scattered in clusters, well then with only one fiber that would run for 100 kilometers, you can monitor several fields with only one readout point. So it had a lot of advantages and assets. Now, obviously, this is working in a lab. This is working at CERN. So as you can imagine, there's a major difference between something that is operating in such a controlled environment as a high-energy physics lab and getting into the field. But that's what we decided to try anyway. The ultimate goal being, obviously, to save water, which was the idea of this talk. So this is the consortium that is behind the project that I set up last year, well, late 15 exactly. So the project is called Force4i. We've got a nice logo. On the academic side, we've got 3 institutes. One is the Lebanese University, based in Beirut, the INFN Naples, and Unisagno, which are universities from the south of Italy. These 2 universities clearly are the founding father of this technology. They happen to be CMS institutes, so they developed this technology for us, but really the IP, the intellectual property, is with them. And the Lebanese University is an institute that joined CMS last year. So these people here are the scientists who are going to inject manpower and ideas into the development of the technology. Because we are not at all into agriculture, we also needed a lot of input from a specialist. And LARI, which is the National Agriculture Research Center Institute in Lebanon, has joined the consortium, and we are dealing there with irrigation specialists. So they are explaining to us the kind of needs that should be taken into account when developing that system. Then we also have private investors. So we got National Instrument Arabia. They joined the project because they felt quite inspired, and what they are doing is that they are training our students, our people, our researchers, providing hardware at cost, essentially, and providing also free consultancy. We have OptoSmart, which is an SME in the south of Italy. They have the knowledge to develop the sensors, to produce the sensors with the coating on top. The UK Lebanon Technical Hub is our funding agency. They are providing 100% of our budget right now, so which is $600,000. For them, this is also an opportunity to show that Lebanon is on the way to become a high-tech driven economy. And finally, there's CERN and CMS. So as I said, what we did was to put the project together, to identify synergies between the different actors, get the funding, so we had to run around and find some money, but also, thanks to our knowledge transfer unit, we framed the project. So there's a collaboration agreement that is defining the responsibilities and how to share the outcome of the project. And this is a nice picture taken in Beirut in January 16, where we all met face-to-face for the first time, even though we'd been working together, 17, so it was this year, even though we'd been working together for almost a year. So just a word on our funders, we owe them that. So this is a business accelerator based in Beirut, and they've got 3 fields where they want to support innovation. So you've got fintech, which is quite far from what we do, visualization, but well-being. And within well-being, you've got agriculture and food technologies, and this is how we fit into their funding scheme. Now, working with Lebanon is not just an opportunity of having collaborators in CMS. Saving water is an existential concern for Lebanon. This is a graph showing you the threshold beyond which a country is deemed to have to be unsustainable in terms of usage of water resources, which is a bit of a pity, really, because Lebanon has a lot more water than most countries in the region. They've got mountain ranges, so they've got let's say a regular supply of water through snowfall and rainfall. They also have waterways, and they have underground water, and they have groundwater. However, there are many problems. Our colleagues from LARI, so this Agriculture Institute, told us that between 70 and 80% of the groundwater has been drained beyond, let's say, in a way that is almost irreversible. They were saying that the only way, in their opinion, to restore that would be to stop pulling water from them for 50 years. So we can all agree that's going to be quite difficult. Most of the coastal area, most of the groundwater is already contaminated with seawater. The idea is that if you deplete groundwater on the coast, then seawater seeps in. Of course, like the previous presentation, the effects of global warming are striking in Lebanon. And also there is significant stress put on the groundwater because of the somehow chaotic way people are drilling wells. Right? So particularly in areas where groundwater is known to exist, there's a tendency to just dig a well and help yourself. So this has been a significant stress because sometimes these wells are very poorly located and contribute to the, let's say, to the unsustainable use of the water table. Also, well, there is aging of infrastructure, so 50% of the transmission and distribution networks have passed their useful life, and there again, this is, let's say, there are many problems in Lebanon, so this will take time to sort out, which means that, in fact, the unaccounted for water levels are 13% higher than the world average. So, yeah, definitely this was very important to save water. Now, on top of it, as you all know, the problem is compounded by the refugee situation. I mean, if you look at the figures from UNHCR, 1,100,000 people are registered as refugees, but for Lebanese, this number certainly is closer to 1.5 to 2 million people. So these are people, obviously, who need water, and that, again, taps into the resources. This is another graph that is interesting. This is from the FAO, and so it is identified that irrigation is the largest water consumer for with low efficiencies. So there is definitely something to be done in Lebanon on irrigation specifically, which means that our project fits quite nicely. And so we believe, at least this is our aspiration, that if we manage to provide a technology that helps rationalizing irrigation, it can make a difference. Again, the idea is to deliver water only when the crops need it. So where are we, and how does that work all together? So the first step was to use our sensors fresh from CERN and see how they were coping with real-life situation. In that case, we didn't go to Lebanon. We got Lebanon to come to us. So our colleagues shipped us 10 kilos of soil from the Bekaa Valley, which is where most of the agriculture industry is located. And we tried our sensors. And that was actually a good call, because one of the specificities of the Bekaa Valley is that the soil has a very high clay content. And this had a tendency to saturate the film through which water was supposed to go and reach our sensor. So already from phase 0, we had to redesign what we call a package. That's something in which the sensor is wrapped. So that was something we did in June and July 16. These are the kind of instrumentation that you use, because this is very important to calibrate. So we wanted to be 100% sure that we knew where the reference and that the response of our sensor could be predictable and reproducible. Now, phase 1. Phase 1 is actually going to Lebanon and installing our sensors there. So this is Beirut, and this is the Bekaa Valley here, and so this is our experimental site in Zaleh. What you see is that we've got a series of sensors at different depth. The idea of this phase 1 is to better understand how our sensors work and what we can learn to make them even more suited for what we're trying to do. So, for example, at what depth should our sensors be for potatoes? That's the kind of data we want, because obviously you don't want to have to install so many sensors for just one field. We want to be able to say, for this crop, you need a sensor at that depth, and so on and so forth. But we also wanted to see whether our sensors could detect water diffusing through the soil and be able to identify, to measure what we call the field capacity. That means that the amount of water stored into a field that can contribute to the growth of this crop. And so this was our technician installing these sensors. The installation was complete late January. And we've been taking data ever since, and this is working quite nicely. There's no point going into further field tests until you've assessed how well our sensors are performing. This is why we give ourselves enough time, like essentially a season, to see how they're coping with very dry conditions to very wet. Because even though this is called semi-arid type of terrain, we had an extraordinary wet winter, which means that our humidity sensor were actually saturated for a long time. So the volumetric water content was higher than 25%. These are the data from last week, just to show that these things do work. So what you see here are the data sent by the deepest 6 sensors that we've installed. This is just one set. We've got actually 4 sets for statistics to make sure that if we see something funny in one set, you can compare with the other sets. So here you can see the temperature, which is fairly stable. As you go up towards the surface, it warms up, which is expected now that we are quite warm. And here it's a nice way to illustrate the diffusion of water. So when you've got, so again, you're going from, so this is the deepest, and this is the shallowest. The idea is that you can see the diffusion. When the top layers are depleted in water, you can see the bottom ones rising in terms of volumetric content. So you see the transition of water through the soil. So this is very encouraging, and we're going to keep running this for whatever time we need to understand exactly what properties we want for our sensors. Phase 2 is very interesting there. This is when we want to go to the farmers. So we go, because this field here, I should have said, this is at Larry, so this is at the research institute. So it's still in a field, but it is, it has infrastructure behind it. Now, what we want to do is to go to farmers. And the idea is that we would select what we call pioneer farmers who are given an incentive to collaborate with our project by the purchase and of drip irrigation systems. And we will choose 3 strategic crops, so potatoes, green beans, and lettuce. Lettuce because this is a greenhouse vegetable, so we want to be able to draw conclusions from different types of crops. And the idea is to have for each crop 2 fields of 1,000 square meter, one installed with our system, so equipped with our system, where irrigation will be managed using our system, and another one which is a reference field, which is a standard one. And at the end of 1 year, the idea is that we want to be able to see how much water we've saved. Our hope eventually that it will be around 20%, but this is still an aspiration. And whether we could measure an increase in the crop yield. That's for sure a very exciting part, but this will only take place once we are confident that we are learned enough from the first phase, where we just deployed our sensors and see how they coped. Another thing that is very important is capacity building. Clearly, the know-how is at CERN and in Italy. Our Lebanese colleagues started from scratch. There was no optics lab in Lebanon, and so we created, through the project, through the private funding, the first optics lab of the country, and this is in Beirut. So these are a few pictures. We injected about $350,000 in there, so a large part of our budget went into building the capacity of the Lebanese university so that they can contribute to the development of the technology. So there is a commitment of transferring knowledge between CERN and his Italian partners to Lebanon, which was also why we get this funding. I mean, this business accelerator are fully aware that on technologies like this that are labor and capital intensive, you need to kickstart the effort. So this is for phase 2. So phase 3 is even more ambitious, but we really believe we can do it. Since you already have on your fiber a temperature and a humidity sensor, why don't you add other sensors that provide a full package solution for the farmers? And typically, what we would like to do is to add on our fibers a way to measure the content of pesticides and fertilizer in the soil, that the farmers will be able to monitor all the parameters that are really of importance for the operation of their fields. So you don't add pesticides if it's already there, or fertilizer if it's already there, or water if it's already there. So this is let's say, what we call a smart fiber, because it's an all-in-one type of system. This is very challenging, and we need a lot of researchers injected into this. So on top of the existing teams, we're going to hire a doctoral student in October. We will be deployed on this topic. Now, of course, if we want to have an impact on Lebanese farmers, or let's say farmers around the world in that region, the costs have to be aligned with the disposable income that they can make. And that's obviously a long way to go, because as I said, the off-the-shelf device is about 20K. So there's no way this is going to fit anytime soon in a farmer's budget. But we do believe that we can rationalize this kind of readout and get the price to dramatically drop, because this device off the shelf as an R&D tool. So they can do multiple tasks. It's a research instrument. What we need in that particular case is a dedicated, it can be a black box, it doesn't need a screen or anything. What we need is a dedicated plug-and-play system. The idea is that we would have a box of any kind, just linked to a smartphone interface. So the farmer does not have to understand anything about the electronics, doesn't have to worry about it. The smartphone interface will tell him the humidity is such, the concentration in pesticide is such, and so on. This is obviously extremely challenging because if the industry has not done it, there are reasons, right? One reason is that this is not a mature technology yet, so this is innovation. So the industry is probably waiting a little bit before getting into this. In fact, National Instruments stopped commercializing these interrogators, which was kind of awkward because they joined the project, but still, we do believe that there's a way to do that, but we're putting a lot of effort, a lot of resources into this. So we've got 3 postdocs hired by the project, again, private funding, starting in September this year. So these postdocs and technical students will be based either in Naples or in Beirut. And in the job description, it's very clear that in order for all this to work, they will be frequently traveling between the 2 countries. And for various reasons. First of all, to share the findings, we really do intend to work as a team. To keep building the R&D capacity of Lebanon. This is very important because this is a partner of CERN, a partner of CMS. This is a country that is financing the project, so we want to build that capacity. Carry out field tests, but also push the boundaries of the technology to see if there are commercial ventures at the end of this. Because if we were to succeed at the end of phase 3, to have a plug-and-play system for, I don't know, a few hundreds of dollars, and if it works, then maybe there's something to be done there. I mean, you know, Lebanese are entrepreneurs. It's in their soul, it's in their DNA. So obviously, this is something that was also a motivation for our funding agency. Can we push this technology to the point where there are some commercial gains to be made? And economic development for the country, also technical development. So this is clearly also on the map. So just a few conclusions. First, we are and we will learn a lot from the phase 1 field test. I mean, this is the first time these sensors have come out of CERN, so out of a lab and into a field, and they are working so far remarkably well. The collaboration between the academic and industrial partners has been fantastic, so which means that the private-public partnership do work. Certainly in our case, I can testify. We are looking forward to the injection of new manpower, because obviously these 3 postdocs and doctoral students will make a huge difference, because they're going to be focused just on this project, and they're going to be, we hope, enough synergies between them and enough momentum that they can really bring the project to the level where we need it to be. But also I would like to point out that this is really a win-win project. The way I packaged it, I wanted every single stakeholder to have a real natural incentive to commit to it. Because for Lebanon, as I said, it's an opportunity to build a capacity in a new technology. There are commercial ventures at the end, and it addresses, let's not forget, their water concerns. So that's all good for them. For Italy, well, for them, it's quite fantastic to get postdoc funded by external money. This was unprecedented for INFN. So here you got a Lebanese business accelerator putting money towards postdocs in Italy. So this was very good for them. And it increases the amount of manpower deployed on this technology, which is their baby. I mean, they want nothing more than more people working on it and pushing the boundaries of that technology. For CERN, it was very nice too. It is very nice too, because it's an illustration of the technology transfer capabilities of the organization. I mean, we're using the famous open hardware license for this project. We're working open source. So the philosophy of CERN to transfer technology from the organization to a wider range of stakeholders is perfectly illustrated by that project. And finally, for us, for CMS, there are also plenty of benefits. First of all, we get good exposure, but also the benefits in terms of R&D of this project can be re-injected into our applications, because right now, like anybody else, we pay our interrogators $20K, which somehow limits the amount of deployment in our detector. Now, if this drops to a few $100s, of course, it completely changed the game. Maybe we can put these fibers in many other places, and we can take advantage of the advancement in let's say the capabilities to detect new parameters. So, what do we still have to do? So, one thing that we learned from phase 1 is that the range of our sensors needs to be increased, because when it's raining a lot, they are saturating. It's probably a combination of the high clay content and the exceptional winter that took place in Lebanon. So we need there to design a new package. The R&D on the water delivery system. So now we are monitoring the water, but you need also to be able to deliver the water in an efficient way. And there, this is outside of the scope of the project initially, but our colleagues are certainly working on this, so Larry and the Lebanese University. And also we'd like to find a way, once this works, to open and close the valves remotely. And for that, we're also working with a third Lebanese university on remote operation. So that's using some kind of wireless system. And finally, still something that we have to do, we still need to find funding for the travel expenses of our scientists, because the project will only cover their salaries and, let's say, the purchase of material, but not travel to present their work at a conference. And obviously for postdocs and doctoral students, this is essential. So, if you have any idea or any interest in helping us with that, that would be most welcome. So that's it. You can follow our progress at this link. This is our website. This is a project website that we update when we've got good results. These are my Italian colleagues, quite happy to have installed their first set of sensors. I'd like to thank the Sharing Knowledge Foundation for the invitation, and thank Patrick for his lasting support. And if you have any question, please. I know it's almost lunch, but you never know.
Okay, good morning. Thank you very much for the interesting introduction. My name is Abraham Tene. I'm a former director of the Israeli Sewage and Water Authority. And just to let you know that an Israeli company called Netafim, who is really the inventor of the drip irrigation in the world, developed a very interesting drip irrigation measuring the humidity, the same idea, measuring the humidity, temperature, and pH, it means acidity, of the root of the plant. Mm-hmm. It means by measuring directly the humidity, they will be able and are able to give the exact amount of water needed. And I think this is really a sharing knowledge that can be between you and this company, and I will be more than pleased to contact you with them.
I'll take you on this, absolutely. Yeah.
The second thing is just a remark about the water in Lebanon. I didn't hear anything about water reuse in Lebanon. And if Lebanon would reuse their sewage, their wastewater, I believe they will have about 50% of the water needed for their agriculture. The same is done in Israel. I'll talk about it in about 2 hours from now. Thank you.
Oh, for sure. I mean, the water treatment is a big thing in Lebanon. My colleague in the Bekaa Valley told me that their parents used to drink the water from the river. When he was a child, he was about my age, he used to swim in the river. And now none of this is possible. So definitely there is something to be done there. I guess it's a matter of priorities. At the moment, the country is under a tremendous stress because of the refugee situation. I guess it makes it fairly difficult to, let's say, to have a long-term policy on this. I mean, everybody is aware of it, that's for sure. And you're right. I went to Oman a few months ago, and 80% of their water is treated and injected into an irrigation system. So this is, I mean, there are solutions, that's clear. But irrigation is probably one of them. We don't have the let's say we don't have the arrogance to say that we have a solution, but we're just hoping to make a contribution to making things better.
Thank you. Thank you very much for the very nice project and product. I acknowledge the importance of these sensors and the technology in controlling and monitoring soil water for irrigation. But you indicated that this is providing water saving. I haven't seen any evidence that you have saved any water by monitoring and controlling the water by irrigation. Of course, increasing yield doesn't mean you are saving water.
Yeah.
More likely that increasing yield means you are using more water. What have you done to quantify the water saved by using these sensors?
So this is one of the objectives of what I call the phase one. So at the moment, we just put our sensors in the soil for the first time in January. So I can't tell you how much we've saved. The ambition is that if you don't irrigate when you don't need to, and which means that either when there is enough water still in the soil, or when the soil is saturated with water, so there's no point of adding more, then you're saving water. So the water saving is just because you provide the water when you need it and not, otherwise it's just a waste. That's the idea. But I'll tell you more, hopefully in a year's time, when we've been able to quantify this.
Yeah, well, I just want to say that saving water means that you are preventing the loss of water. And
the what, sorry?
The loss. And where do the water go if you are losing it? The general perception is that if you irrigate a lot, that means you are losing lots of water.
Yeah.
Or if you are irrigating, but the water sometimes join the groundwater or go to the neighbor or stay in the soil. So the quantification of water saving itself is required to claim that any technology can save water. I don't think the sensors and the monitoring of the soil save lots of water because the water is recycled in the system. Even if you think that you have lost it in this place, you are gaining it in some other place. If you deep percolate it, you can get it in the groundwater. If you run off, you are getting it in the downstream. So I would like to just point out that when we use water saving, it is a very sexy thing to say about technologies, that it saves water. But in most of the cases I've seen, it is not a saving of water. It's increasing production, it's improving yield, it is preventing others, but not saving water per se. Well, and that's my comment.
Yeah, thank you. Yeah, I mean, you're assuming that if the water is used when it's not needed, that it will go back to the groundwater, yeah? But that's only if your groundwater is in a way to be exploited. Because if you pump from somewhere where you've got clear water and you waste it on your field and then it reaches groundwater that is either contaminated or just unavailable, then you've lost your water. Yeah? So of course, each field will have a different configuration, but not using water when you don't need to is a saving. So, we can agree, we can maybe have different ways of saying that, but certainly for a farmer, it's crystal clear, because if he is paying for water. So, I mean, saving water, we could go further into the definition, but the idea that the water used to reach an equal yield should be less. In that sense, this is, I guess, the primary definition for us of water saving. If you've got a healthy groundwater, I agree with you. It's
You said that one of the major savings for Lebanon, the greatest water use. Thank you very much. In your earlier presentation, you said that irrigation is the greatest water use, water consuming avenue for Lebanon, and that groundwater depletion is a huge problem, and mainly from private wells. Yeah. Looking at the cost of this investment and this research, I'm wondering who your target population are, who are going to be the users of these technology, provided that if you're really aiming to save it from private wells and from private farmers and irrigation losses, how will this be affordable? And does your next research include that component of making this technology usable by many farmers, private farmers?
So, at the moment, the project is funded for 3 years. The idea is really to focus on developing the technology, because it's already a handful. I mean, this is extremely challenging. I believe that my Lebanese colleagues will then look into that sort of things. But right now, the ambition is not there, I mean, for the 3 coming years. Because this is water management. This is really out of the scope of what a bunch of scientists can do. But you're completely right. I mean, if you want to be efficient, you have to have the full supply chain targeted. At the moment, the target population would be farmers who have fields scattered over tens of kilometers, and having the means from one single location to see how their fields are doing, essentially, how much water you've got in the soil of their fields. That's the scope for now. So down the line, if you think about commercial applications, for these people to be potential users, of course, we need to dramatically drop the price. And this is the ambition of Phase 3, where we got these 3 postdocs working on it. I mean, this has never done before. You know, this is I'm not pitching a product here. I mean, I'm really trying to say this is a technology that we believe has a lot of potential, but it is going to be labor and capital intensive. There's no question about it, because you need to spend time in the lab, and not just any lab. You need to spend time in a lab that is really equipped for that technology. Yeah? The investment down the line will not just be for irrigation, because once our Lebanese colleagues are at the state of the art of that field, they can develop their own sensors, if you like. But the target population, I'm hoping, as wide as possible, particularly if there was some kind of funding scheme attached to it, a subsidy scheme.
Okay, thank you very much.
But I'm happy to...
So we can still have the discussion during lunch.